Chapter 7 Alkyl Halides. Seven point one is about substitution and elimination reactions. So what are the reagents like hydroxide used for, and what are their issues? Hydroxide like NaOH is considered a strong base, and when competing between substitution and elimination reactions, it can get quite confusing. So we know that we need to answer, first of all, what are they used for? Strong bases are used for elimination reactions. Strong bases are used for elimination reactions. And what do we know about strong nucleophiles? Nucleophiles are used for substitution reactions. Not that we got that. So we need to answer, does NaOH, is that strong base or strong nucleophile? Well, it turns out it's both. And so following that, to answer what are good substitution elimination reagents, we need to know what are good reagents, good leaving groups. Good leaving groups include those with conjugate bases. Good leaving groups include those with good conjugate bases. Of strong acids. Good leaving groups include good conjugate bases of strong acids. What do I mean by that? Well, we learned that whenever a reaction proceeds, it steers away, or the equilibrium shifts away from strong acids. Remember, strong acids react with, I would say, either weak or strong, but let's say strong base. And so if either of these, the acid or base, are strong, it will shift the equilibrium so that it will form a weak acid and a weak base, otherwise known as weak conjugate acids or weak conjugate bases. That's just the nature of the laws of thermodynamics, which can be explained later. Now on to part 3. Now we need to come up with good pKa's to compare if hydroiodic acid is a good leaving group compared to ammonia. So hydroiodic acid versus ammonia. Well, we know that the conjugate base of hydroiodic acid is a very stable, compared to the very reactive conjugate base of ammonia. Now this is very reactive. Reactive means it's a very strong base, right? Because strong bases want to react a lot. So that does not mean that this will shift in this direction. It rather would go back to the ammonia form. And that is why we get when discussing good leaving groups, we know that hydroiodic acid is the answer, because it will want to deprotonate remember, leaving groups. What are leaving groups? Leaving groups are where there's a molecule and there's a part of the molecule that wants to leave, but if it wants to leave, it probably would have to give up that hydrogen and turn into the conjugate base. The conjugate base is this one here, very stable, also known as very weak. Very weak means very stable. That's why it'll go in the direction that's desirable when that defines as a good leaving group. So, good fact to know is that leaving groups tend to have a pKa that's less than a 0. And so let's discuss why. Well, if the pK of anything is less than 0, that means it's a strong acid, right? And if it's a strong acid, just like how hydriodic acid is a strong acid, it'll tend to shift the equilibrium forward, or I would say to shift forward or to its conjugate base. And if it goes forward, and whichever way it's going towards, it always goes towards the weak acid or the weak base, and that's why we know it's the conjugate base of hydriodic acid. Alright, moving on. We know that the good leaving groups shift the equilibrium forward into its conjugate base, which is probably a weak or very stable. So we got that. Now 7.6 is about the stability of alkenes. Stability of alkenes. Now, that's number 4. And so what are the 2 factors that contribute to stability of alkenes? 2 factors that contribute to stability of alkenes. Stability of alkenes. What are the 2 factors that contribute to stability of alkenes? Now, what makes an alkene stable? Well, we know that there's 2 factors. One is steric effects. We'll explain this in a minute. Or 2, it's known as degree of substitution. Degree of substitution. Now let's explain what this means. So let's say there are these alkenes, okay? And depending on whether they're just hydrogens or if they have one alkyl group represented by R, so R just means like continuing lines, which stands for just carbons, extended carbons, and the rest is hydrogen. So this would be monosubstituted. We call this monosubstituted. Now, comparing just these 2, this would be called ethene because it's just all hydrogens on 2 carbons. So would the ethene be more stable than the monosubstituted, or would it be the other way? Actually, it's less substituted, less stable. It's much less stable than the monosubstituted. And the reasons for this is I'm not too sure. Well, in the answer key it says it's due to electronic effect. Well, we just need to know that according to the laws, higher degree of substitution means more stability, higher stability. Higher degree of substitution means more stability. So that means because we have one more substituted part of the molecule than this monosubstituted. So now you could probably guess the next trends will be the next stable. The next stable would be disubstituted, but again, What does disubstituted mean? Disubstituted. Disubstituted. Basically, it just means as long as we have two R groups on any of these chains, we know it's considered disubstituted. So there's three different variants as we turned out. For example, they could be on the same side, known as cis, where both R goes, and again the remaining is just H. Or there's also trans, which means diagonal, and then the hydrogens fill in the rest. Or there is like this form. There's no specific form. Sorry, there's no, I thought there would be no term, but it's called geminal. Geminal just means on the same carbon there's an R group on both. So it turns out cis is less stable than trans, and trans is less stable. Trans, again, I told you, means opposite of one another diagonally. Cis just means on the same side, and trans is opposite. And geminal means that on the same carbon, there's both R groups. So geminal is more stable than trans is more stable than cis, as noted by these arrows. Now, so what's more stable than disubstituted? Yes, it's trisubstituted. Trisubstituted. Now, what does that mean? It means there's three R groups on the alkene. That means there could be, it goes like this, and there's only one hydrogen attached on that alkene. And then at last you would guess correctly that it's just tetrasubstituted. There's no hydrogens, it's all R. So let me explain this forward. This direction means it's more stable. So tetrasubstituted is more stable than trisubstituted, is more stable than disubstituted, and within disubstituted there's geminal, which is the most stable, both same on the same carbon. Trans means, again, just opposite. Cis means on both sides. That's more stable than monosubstituted. And then at last, the least stable is ethene. Okay, now point number 5. Now this point number 5 is part chapter 7.7, radioselectivity of elimination reactions. How does the steric hindrance and size of base affect the elimination reactions of alkyl halides? How does the steric hindrance and size of base affect the elimination reactions of alkyl halides? Let's look at the notes. Okay. Well, before we get to 5, let's do some practice. 7.10, conceptual check. Now, you need to tell me which of these is the most stable. Now, we learned that, again, if we're talking about stability, we were looking at R groups, right? So looks like R just means they're extended carbon chains. So in terms of counting R, there's 1, there's 2, 3, and 4. Because these are not hydrogens, remember, these are just carbons. That's where this one. This is tetra. And we learned that tetra is most stable. You could just look above, I have in the arrows, most stable. Now, what is this? Yes, this is disubstituted. There's only 2 R's, right? These are just hydrogens, so they don't really count. And so it's disubstituted. Now, I told you on disubstituted there's 3. Now, which one of these is most stable? It's geminal diol. Geminal is most stable of disubstituted. Now, is disubstituted more stable than tetra? Well, you learned tetra is most stable, so definitely not. This is much more stable than disubstituted. Now, comparing this is just comparing these two. And now let's look at this. This is how many R's are there? 1, 2, 3, and 4. Interesting. Sorry, there's not 4. There's actually just 3, because there's 1, 2, and 3. This is just hydrogen. Tri-substituted. It's tri-substituted. Now going up the ladder, we learned tri-substituted should be more stable than di-substituted. Okay, so I was saying stability, most stable. This is most stable, and then tri-substituted second most, and di-substituted is the least stable. Moving on, this is question part. What is this? Right, we're back at question part 5. Now, how does steric hindrance and size of base affect elimination of reactions? What do I mean by that? I said strong bases make good reagents for elimination. And so if we look at 5, right, so let's look at this example. For example, if we had this and we reacted with a strong base, then we could get either this or this. Why is that the case? Because we learned elimination goes from alpha to beta, which basically means that this is a leaving group, so it goes away, and then towards from alpha to beta, it'll make like a double bond. It'll go like this, or it'll go like this. And so that's why we get both of these. So we need to know which one's the major product in these type of questions. So let's say, how do we determine which one's major? It turns out there's a term for this. This is called Zaitsev. This is called Hoffman. Now, how do we classify between the two? Zaitsev just means it's more substituted, and this one is less substituted. Turns out we get different percentages depending on the reagent of base. Now, one thing we need to note is if the base is like ethoxide, then this is considered small sized. Other words, the lowest sterics. What does that mean? It means that whenever it approaches the hydrogen of either beta carbons, it will have least things getting in the way, and so in this case the Zaitsev will be the majority, 70 majority. Hoffman will be minority. Using this logic, if we move on to largest sterics, in other words, this means most bulky base. And let's say the most common example is tert-butoxide, or it's also this molecule. This is not tert-butoxide. This is something bigger than that. But there's a lot of stuff for constituting this base. So what happens then? Then the Hoffman is the majority. So again, larger sterics favor Hoffman. Smaller sterics or less bulky favors Zaitsev. Zaitsev because Zaitsev just means it's more substituted, And it would make sense, right? Because if it's smaller, then it could really squeeze in the beta carbon over there. But if it's very big, it would prefer like the outside portion, right? Um, yeah, I think that would make sense. Sorry, was I looking at the wrong carbon? No. Yeah, just know that the bigger bulky bases prefer the Hoffman product, which is um, less 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 substituted alkene. Remember we were talking about alkenes. This is disubstituted because it's the geminal, remember, and this is tri-substituted because there's 1 2 3, and it just makes sense when you think about it. Tri-substituted means it's more substituted, and that would be favorable for small bases. If it's a very big base, then obviously we want the lowest substituted because yeah, you get it. So there's that, and there's tert butoxide. Now I'll let you answer this question. I'll hint you this falls more along the larger base than euthoxide if it's larger. This is 8%. Now, so which one is it? Is it Zaitsev or Hoffman? Well, turns out it's closer to being classified as a bigger base, and that's why it prefers Hoffman. 72% major, and Zaitsev is 28%. All right. No. The question is 6. If we have this molecule and then an AOME methoxide, we react with methoxide. Would this be what would the product be? Remember, we could get either products, this one or that one, but it would just be this one because it's symmetrical. It'd be like that, and then we get a double bond. So what would the answer be? Turns out the answer to this is, I'm not too sure. Well, looking at the key, looks like this will be elimination 2 reaction. So to answer this, we need to determine, is this a bulky base? Turns out it's not, because methoxide is not sterically hindered, and that is why this will be considered the Zaitsev product. All right. Seven. How does stereochemistry affect selectivity of elimination reactions? So stereochemistry affect, what do I mean by that? Stereochemistry just simply means whenever a reaction occurs, it could be cis or they could be trans. R prime just means it's not the same alkyl group as the alternative. This is cis and this is trans, and if in a reaction we get either of this, we basically want to say it's trans. This is gonna be more favorable um, for the selectivity of elimination reactions. Well, now why is that? We learned that by Hammett's postulate. This is a very bad overview, but when we compare the transition states, we will learn that cis is higher and trans is lower. Now, the laws of thermodynamics, or was it kinematics, shows us that we want an activation energy that's lower, because the lower it is, less energy input we need. Trans happens to be lower, and that's why whenever we get elimination products that's possible, like these kind of stuff, and we have to consider stereochemistry, it's always the trans. Note that E2 can only occur on sp2 hybridized. Okay, lecture 8. What makes E2 special and unique? We just answered that. It occurs, elimination happens on sp2 hybridized or vanillic halides. That was a brief overview of chapter 7, and now we will go on to chapter 9. Chapter 9.